All right, so I'm gonna go over section 1 point or 6.1. So I'm gonna just like go through the chapters because uh, sometimes I zone out during the book, and I'm like, oh yeah, I understand, and then I try to do the questions, and I'm like, whoo, never read this before in my life. So I'm just gonna sort of like go through and have notes, just so it's like easier to understand than just sitting there reading the textbook. Um, so basically, section 6.1, what I discovered was a section of almost. So it's almost going to solve two problems, but not really for either. And it's definitely not going to solve the first one because it's going to stop the first one really quick and then jump to the second example. And then it's gonna sort of loop back around. So you're really doing the first example to help you with the second example. You're doing the second example to help you with the next section. So we're just gonna, this is basically just background. Um, so here is kind of what that section was all about. Um, share that screen. Okay, so the first example it has us do is the shortest path between 2 points. So we know that that's going to be like a straight line right between the two paths or the points. But we're going to pretend that we like fell on our heads. We don't know that, and we're just kind of stumbling around. So we would like to find the shortest path. Um, so in order to do that, we're just basically for this problem, we're just going to look at the shortest integrals um, between the two. So what we're going to do is basically along this path, if I can get it to draw, we're going to pretend that's really on there and that for short segments of time, it acts as a straight line on the path. So with this, we're going to call that line ds. And pardon my bad OneNote skills, but basically with ds, we're going to use Pythagorean theorem to say that ds is going to be equal to the square root of dx squared, come on, plus dy squared. So that's basically all we're doing there. But the awkward part about that is then we have two unknowns and one equation, and that's just like not the vibe. So what we're gonna do is we're gonna take ooh, funny. We're gonna take hey, stop doing that. Okay. We're gonna take this dy and we're just gonna make it in terms of dx since we know that y is the um, dependent variable and x is the independent variable, sort of just on this graph. So what we're gonna write for dy is we're just basically gonna tell the definition of dy, which you can get by doing dy dx times dx, which you'll see these kind of like cancel and you end up with dy. If I were to do that, I don't know. My stylus isn't the best. But anyway, you can rewrite that as just y prime of x dy, or not dy, but dx. Here, I'll write that over here so that it's all the way on. Um, and basically, what we're going to do is we're going to take this right here and we're going to plug it back. I'm just going to draw over it. We're going to plug it back into that equation. So in order to do that, I'm going to scroll down so we want to remember those two. And we're just going to rewrite ds over here. And ds is now going to be the square root of dx squared plus y prime of x squared and dx squared. So I'm just sort of distributing the square there real quick. And then we can actually pull out these dx squareds and pull them completely out of the radical, but we're going to put them in the back just for consistency with the book. And what that lands us with is that the ds will equal 1 plus y prime of x squared and under all that. So, and then the radical will be times dx. So that's basically as far as they take this problem. And then what they're going to do for the next problem, we're actually going to set that up here, is if we bring that down, the next problem is called, let's see, it's called Fermat's principle. And what this does is it basically deals with light. So we know that light will travel, I'm just making it easier for y'all to see. Light will travel using its like the fastest possible path. So we're basically going to use that to represent traveling in different speeds and different mediums, which a lot of things do, even us. Like that would be the problem we did in class where you're running on the sand and then you're running in the water, like your lifeguard on Baywatch. So that's this, but we're doing it with light, so that it just flows a little bit better with modern physics. So in order to do that, I'm gonna draw y'all just a little picture, and hopefully it turns out well. So this is gonna be my glass prism. I'm gonna give it some, that's how we know it's glass, because it's gonna glow blue. And then around it is gonna be air. And there's air. It's just gonna be clear. And so I have a beam of light coming in, and then it enters the glass, and then it exits. So that might not be most accurate, but that's basically what light does, is it bends in each one. We all know. Okay. So what the book calls Fermat's principle is really just stating the obvious. So what this is ingenious, but what the book does is it says, so you're traveling through from one point to another. So let's say like this point to this point, and you're like, what's okay? Maybe out here. Doesn't like me right now. To that point, that intersection. It's like, what is the fastest way to get there? And so what it's saying is that the path you are on from point 1 to point 2 will have a total time that you travel on said path. Um, and that's literally like your total time will equal the time you spend on the path, is what Fermat's principle is stating, like right out in the book. And then they go on to further it, but it's kind of just ingenious because if you think about it, what they're then saying is that your time t and whichever path you decide to take. So I'm going to put P for like just an arbitrary path. Your path 1, it takes a lot of time. It's up here. If it would ever cooperate, we're going to do a small, it's up here. Your path, I don't know, 7 also takes a long time. So it's going to be up here when it decides to like me. And then your path 4 is somewhere in here, and you end up like this, and you have a minimum of this function right here. And whatever this function's minimum is the minimum time you can spend traveling any number of your paths. So it's just looking for, by definition, the shortest path. Whatever path takes the least amount of time is what's going to be produced by this. So with that ingeniousness, we're going to write it down a bit more. So they play with it based on light. So from point 1 to 2, there will be a time difference, and the total time is that integral. And that will be equal, again, from point 1 to 2, ds over b. So your displacement over your velocity is the time it took you, or the distance over your velocity is the time it took you to do that. That's all that says right there. And then applying it to light, we're going to use the index of refraction equation. So basically through that, we know that E equals C over N, and N's the index of refraction, C is the speed of light. So we're just going to rewrite this. But what we want to keep in mind for this is that N can vary and C is going to be constant. So since it's 1 over V, we're going to flip the whole equation, and I'm going to take 1 over C now outside of the integral, just so I know it's a constant. I don't forget that. And we're still going from point 1 to 2, and we're going to use, so then n is left in, but the thing about n is a function, and this function is going to be in terms of x and y. So the n at any given point depends on its position. So if it's in the air position parts, it's going to have a different n than in the glass position parts. And that's the tricky part right there, because it's still times ds. So now what we want to do is get it out of the ds variables. So we want this part right here gone, and we want to keep x and y variables. So in order to do that, we're going to pull out from the first example, this ds equals the square root of 1 plus y prime x dx. And using that in this, we're just going to plug it in so that this total time is going to be equal to this with that substituted into it. So I'm just going to write that out for y'all. Whoa. Just going to write that out. So your total time from point 1 to point 2 is going to be equal to 1 over c of going from x1 to x2, because there's our little change of n times x, y, and then the ds we're replacing with this. So we're getting 1 plus, oh my plus y prime of x squared, bad computer, squared times dx. And that is a doable integral, given that you will know your function of n. And that's really where this entire section stops. But basically what this equation that we've produced right here is that the quickest path will have a minimum time. So the quickest path will be the minimum of any time you could spend taking any number of the paths. And it will be the same as the minimum of this function right here. So that's all that this chapter or this section goes out for. And in the later sections, it goes back into sort of what to do with that new knowledge you've done. So this was just like the beginner's package, and the next ones will take you on to more like, what is a Lagrange Euler equation? Why do I care at all? So that's section 6.1. Hopefully that was helpful.